Okay, good morning again. This is Professor David J. De Los Reyes. Okay, it's September 13. The time is 12:39 a.m. Oh, I am here in Los Angeles, USA. Okay, good morning. My topic for this session will be AC machines, and this will now be lesson number 9. Oh, we are running smooth. We are still on transformer. There are so many topics on the transformer. So before we proceed with the alternator concepts and operations and computations, we shall do transformer. Okay, let's proceed. The subject matter for this morning will be a long video format discussion on alternating current machines, and this will now be lesson number 9. We are running smooth. Lesson number 9. The title of the topic is Voltage and Current Vector Diagrams and Equations. If the power factor of the load that is connected on the secondary is lagging. The load connected at the secondary, okay, should have a lagging power factor. Okay, this is Isabel. I didn't place anymore the diagram for the primary and secondary. So the diagram from the previous lesson number 8 will still be the same. We are just continuing the discussion, but the difference now will be the last time around the power factor of the load is actually unity, meaning it's a pure resistance load. For tonight, we will try to bring out the vector diagrams and voltage and current relations if the power factor is lagging, meaning Z here there will be an R plus J exponent. It's an inductive load, so meaning to say it could be motor loads, many motor loads maybe. Inductive load are motor loads. Okay, I will try to erase this one so it will look good. Sorry for that one. Right? Okay, let's proceed. To bring out the vector diagrams, okay, on the secondary side, okay, on the secondary side, there is the so-called E sub S, B sub S, and I sub S, right? E sub S is actually the induced voltage on the secondary is termed to E sub S. This is the load, right? And the current going out is I sub S. But in our computations, we must have to take into consideration the resistance and impedance drop of the winding, because there is no such thing as a perfect winding. There should be a small resistance and a small inductive reactance. So there is actually an R here and X sub L. So this is R sub S and X sub S. The vectorial sum of this is actually the so-called impedance drop on the secondary. So there should be an A sub S, there should be a B sub S and I sub S, R sub S and X sub S. So we will be discussing the relations of all of these. Okay, it's a storytelling, but it's actually the concept on how to bring out the computation. It's like this. B sub S is always with angle 0 degree. It is this, right? And if the current drawn by the load is with the lagging power factor, if we try to bring out the vector diagram of this, it should be this vector diagram here. Okay, it is below B sub S, and the difference in angle is actually the angle of lag, angle of lag. There is an angle of lag. It should be a negative value. So this is actually negative theta. So the location of I sub S and the pictorial diagram is this one. Its location is actually designated, whatever is located from B sub S with an angle negative theta. The difference in angle between them is actually negative theta. And that is actually the angle of log. Angle of log. Right? That's the angle of log. Okay? So if this is I sub S now, in parallel with the I sub S will be the drop across the resistance. This is I sub S, and the drop due to the resistance is this one. They are in parallel, okay? Okay? So this one is parallel with this voltage drop. Because the product of ISRS is actually the drop, okay, due to the resistance of the coil. And perpendicular with it is actually the product of I sub S and X sub S. Okay? Because an impedance drop consists of a resistance drop and a reactance drop, right? And they are perpendicular with respect to each other, right? So the vectorial sum of ISRS plus J I sub S X sub S, it is actually this one. The triangle portion. The triangle portion is actually the product of IS times C sub S. Okay? So if we now try to add B sub S plus I sub S, R sub S plus J I sub S, X sub S, what will come out is actually E sub S. E sub S is this one. Okay? So the voltage across this is B sub S. Okay? We add this one to the impedance drop, and that is actually equal to E sub S. It is this. So the correct vector diagram of the voltage and current relations, considering the secondary side, it is this. Okay, I will try to erase this one so it will look good. Right? Okay, I will repeat it before we go to the primary side. This is B sub S. It is at an angle 0. At a certain angle negative theta, that will be I sub S. Okay, if we try to draw the voltage drop due to the resistance of the winding, it is this one, right? It is this. They are in parallel with respect to each other. And perpendicular with the voltage drop ISRS is actually the voltage drop due to the reactance of the coil, of the winding, right? It is not same as this one because this is a reactance, this is a resistance, right? So they are actually complex number. So the vectorial sum of BS plus ISRS plus J I sub S X sub S is actually E sub S. And it is represented by, sorry for that one, I dropped my cover, it is this. Okay? So the equivalent of that vector diagram, okay, actually we could formulate our own equation, and that's why I place it here. Our title is the voltage and current vector diagrams plus equations if the power factor is lagging. Lagging, this is a negative angle theta. The current lags the applied voltage B sub S by certain negative angle theta. So the resulting equation now, okay, next topic, it is this one. Okay, that is the induced voltage on the primary should be equal to the terminal voltage at the load plus the vectorial sum or vectorial product of I sub S times the quantity R sub S plus G sub S. And this combination here is actually the so-called impedance drop, right? It is the voltage drop due to the negligible resistance of the winding plus the negligible resistance of the reactance of the winding. Because whether we like it or not, there should be a reactance for the winding, right? And how could we compute for the current? The last time around, I forgot to bring out the formula and how to compute for the value of I sub S. For I sub S on the secondary side, okay, just take the kVA rating of the transformer multiplied by 1000 to convert it to volt ampere, okay, divided by the value of B sub S. because the product of voltage times current is actually apparent power. And this apparent power is actually in terms of kVA. But this is only volt in ampere, so we must have to multiply this by 1000 for it to be consistent to be a volt ampere. So this is there is a multiplier times 1000 with the rating of the transformer times 1000 over V sub S, and that is I sub S. So this is now the voltage and current relations considering the secondary side, and the vector diagram is this one. Oh, I will just repeat it, a bigger one. B sub S will be like this, then I will erase it later on. Okay? I sub S lags the applied voltage. This is B sub S. This is the angle of lag. This is I sub S. Oh, this is just a rough drop, okay? And in parallel with I sub S is the voltage drop due to the resistance. So this should be I sub S, R sub S. And perpendicular with this I sub S, R sub S is actually the effect of the reactance. This is I sub S times X sub S, right? So the vectorial sum of IS, RS plus this is actually termed to as I sub S, Z sub S. So the vectorial sum of BS plus I sub S, R sub S plus I sub S, X sub S. Okay? If we now try to connect this one, this is now E sub S. Right? It's the biggest voltage on the secondary. The induced voltage on the secondary is the biggest one. This is small, okay? Plus this, it's equivalent to ES. It is this. So this is how we arrive at this vector diagram. This is the, what you call this, the secondary voltage on the secondary. The current lags the secondary voltage by a certain angle theta. The power factor is lagging, right? And parallel with I sub S is the product ISRS. Okay, perpendicular with ISRS is actually the product ISXS. Okay, the vectorial sum of these two is termed to as ISC sub S, the impedance drop on the secondary. So the vectorial sum of BS plus ISRS plus J I sub S X sub S represents E sub S, the induced voltage on the secondary. Okay, that's how we arrive at this. I just enlarged it. Okay, next one. So we now know the vector diagram on the secondary. These are the voltages of the current and voltages of equations for the voltages and currents. So let's proceed with the primary side. For the primary side, it's still the same. That's why I separated the vector diagram of the primary and secondary, because if we try to merge it, it's a complicated thing. So what I did is that these should be the primary vector diagrams. Okay, I will just put it here, but not totally, so we could visualize the vector diagrams on the primary side. It's like this. This is our computed E sub S on the secondary, right? So if we try to refer this to the primary side, okay, we will take the reverse of this. If this is plus, we will take the reverse of that. It will be this one, this value here. Okay, so this should have a negative sign over here, negative, because this is plus. And if we try to take the equivalent of this in terms of primary, it should be A times E sub S, whatever the computed value of E sub S. We multiply that with the ratio of transformation, but there should be a negative sign because it's opposite, right? So this is not the equivalent of E sub T, okay, based on the secondary computed E sub S. Because as we go to the primary, okay, all values to the secondary, we try to solve back, okay? So we could carry the values that was computed in the secondary to the primary, okay? So this is now E sub P, okay? Let's try to compute for the total primary current. For the total primary current, it is like this. This is I sub S from the first figure, right? If we try to take the reverse of this, Okay, if we try to refer this to the primary side value, it will be its value on the secondary divided by A. Okay, but there should be a negative. So actually, it's like this. Okay, I just enlarge it. This should be this one. It's the reverse of this. It should be negative IS over A, right? And if we try to compute for the no load current, okay, we must have to take into consideration the no load current, the hysteresis in eddy current. We have done that before, right? Hysteresis in eddy current, it is something like this. They are perpendicular with respect to each other, right? Right? This is hysteresis, this is eddy current. Vectorial sum will be this. And that is termed to as I no load. Okay? So if we try, I didn't totally put this one because it's very small already. It will come out like this. Right? So this should be I no load. So to take the total current on the primary, okay, we take the vectorial sum of the no load current plus the primary current due to the secondary current. And it is this. So we will take the vectorial sum, draw a line parallel with this one, and draw a line from the tip of this parallel with this one. Okay. So the vectorial sum of the no load current plus the primary current based from the secondary value, it is this. Right? So this is now the total primary current. Okay? This is a bigger current now. Right? Because the total current on the primary will be the no load current plus the current due to the secondary current, which is referred to the primary. And if we now try to bring out the vector diagram, it is like this. Okay, I'll try to remove this one now. So this is now the total primary current. Okay, so to take the voltage drop on the secondary, or primary rather, on the primary side it is like this. Right? This is RP, this is XP, this is the B primary, right? It's B primary. And the current going in is actually I primary. The voltage induced on the winding is actually E primary. Right? So we now know the total primary current. So to draw the voltage vector diagram of IPRP, this IPRP should be parallel with the total current. Okay? This one. So this one here is parallel with IP. And this is the product of IPRP. It is the voltage drop due to the resistance of the primary winding. And perpendicular with it is actually the impedance due to the reactance of the primary. It is this. Their angle is actually 90 degrees with respect to each other. Actually, the vectorial sum of the two is actually this one. And this is actually I primary times RP plus Gx of P, J. Right, this portion here. So the vectorial sum of this voltage here, the primary induced voltage, plus IPRP plus ISSXS is actually B sub P. This is now B sub P. It is this. Okay, it is this. So this voltage here is the one across this. It's the biggest voltage on the transformer if there is a load. Because a bigger voltage, there will be a drop, it will become smaller, it will be transferred to the secondary. So on the secondary, this becomes smaller, right? And there is a drop again over here. Okay? So B sub S is actually the smallest. You got what I mean? Right? Big one should be less by the product IP RPXP. This becomes smaller. It will be transferred to the secondary due to the ratio of transformation. There will again be a drop over here. So what comes out here is the voltage across the secondary or voltage across the load. That's the one we are using at all. And this is actually the smallest voltage. And for utility companies to make this one a perfect 120 volts, okay, there should be a good designer, okay? Because we'll start from the primary, we move it to the secondary, but the computation is actually, we will start with the secondary, then we'll go back to the primary. So actually, this BP here is the one coming from the transmission line, right? So if this BP here is very small, of course, the output to the one going to our houses is very small. So utility companies make it a point that the voltage on the primary should be stable enough. Stable enough. Okay? If it's not stable, if it's fluctuating, of course, our voltage to our houses will not be exactly 120. It might go 115, and that is considered brownout. Any voltage less than the nominal voltage 120 is considered brownout. But if it is zero, that's blackout, right? So there is such thing in the so-called study of transformer as the so-called voltage regulation. Next topic, there will be voltage regulation for transformer. If the voltage regulation is low, okay, the performance of the transformer is no good. Okay, that's it, guys. Good morning from Los Angeles. This is Professor David J. De Los Reyes. This is the topic, voltage and current vector diagrams and equations considering a lagging power factor load. Okay, good morning from Los Angeles, Professor David J. De Los Reyes.